first, and then.
Hi, everybody. So please join me in welcoming our MLFL speaker for today, Gedas Bertasius. Gedas is currently a postdoc at Facebook AI working on computer vision and machine learning problems and previously earned his PhD at UPenn. Today's talk is on one of his main research interests, video understanding, and we'll be learning about video understanding models that leverage both computer vision and language techniques. Please feel free to unmute and welcome our speaker.
Thank you for the introduction. Today I'll be talking about some of my recent work on video understanding with modern language models. And let me start this presentation by showing you a couple of videos. And so let's start with this one. And don't be surprised if you can't hear any audio, because that's how it's supposed to be. So let's take a look. So after watching this video, if somebody asked you a few questions, for example, who is this person? Who is he talking to? Where is he now? What's his occupation? Probably most of you wouldn't be able to answer any of these questions unless you're already familiar with this TV show from before. So let's take a look at another version of the same video now that also has an audio.
Hello, sick people and their loved ones. In the interest of saving time and avoiding a lot of boring chit-chat later, I'm Dr. Gregory House. You can call me Greg. I'm one of 3 doctors staffing this clinic this morning.
So as you can see now that we watched this video and also heard what this person is speaking, we can answer all of these questions much more easily. So we know that he's a doctor and that he's currently talking to his patients and that he's in the hospital. And so this example motivates the point of this talk, which is that in a lot of video analysis tasks, we can't really solve these tasks just by leveraging video modality alone. And sometimes we also have to use other modalities as well, for example, language in this case. And so this is going to be the main focus of this talk, basically how we can incorporate modern language models to develop better video understanding frameworks. And specifically, we'll be looking at this problem from a few different angles. So first, I'll be exploring this idea of how we can apply language models to the video domain. Afterwards, we'll look at the second theme, which will be how we can use speech from the video to supervise our visual representations. And lastly, I will then finish presentation by presenting this higher level video understanding framework, which we kind of view as a language generation problem. So that's going to be the outline of the talk. And let me first start with this first topic of applying language models to the video domain. So in this case, we'll be looking at a supervised video classification problem. So the goal, given a video, we want to classify that video into one of the human action categories. So just as shown in the slide. And before I start talking about the methodology that we're going to use for this problem, I briefly wanted to take a step back and talk about modern language models, which kind of serve as an inspiration for the model that we're going to be proposing in this part of the talk. So as you're all probably familiar, in the last few years, the field of natural language processing has been revolutionized by these self-attention-based transformer models. And so their simplicity, their ability to learn from large-scale data, and most importantly, their ability to capture long-range dependencies in the data is what makes them so appealing and so effective. And so at the moment, these self-attention-based models define state-of-the-art for lots of natural language processing tasks, such as question answering, text generation, machine translation, and so on. So what is actually the self-attention mechanism? So at a high level, it's a very simple idea. So basically consider that as an input, we're given a sentence as shown in the slide. So what self-attention allows us to do, it allows us to gather relevant context from the entire sentence and then incorporate that context into the feature vectors associated with the individual words. And more concretely, for example, consider a word Bob in the sentence. So self-attention would allow us to incorporate the context from the entire sentence, Bob is a student, into the feature vector associated with the word Bob. And why would this be useful? Well, now if somebody asked us a question, what is Bob's occupation? Just by simply looking at this individual feature vector, we would then be able to tell that in this case, Bob is a student. And so, of course, so this ability to capture long-range dependencies among words is what makes these transformer models so effective. And so, of course, in this case, we could do this also for every other word in a sentence. And technically, the implementation of self-attention is also very simple. So it's nothing really more than a weighted feature averaging. And so we can even take a step-by-step look at how this is implemented. So X here depicts a 2D feature matrix at layer L, where every row represents a D-dimensional feature vector associated with one of the words in a sentence, so assuming n words. Then we have these 3 learnable projection weights, which basically allow us to map this initial feature matrix X into some intermediate feature space. And in a literature, these are commonly referred to as query, key, and value matrices. And they're simply obtained by performing matrix multiplication between this matrix X and these learnable projection weights. And lastly, the self-attention operation is implemented using the scale dot product attention, which consists of 3 operations. So first, we perform a dot product between matrices Q and K. And this basically computes pairwise similarities between every single pair of features, or in this case, every single pair of words. Then we use softmax operation to normalize the similarity matrix to make sure that every value in it maps between the range of 0 to 1, and also to make sure that every row sums up to 1. And the last operation is just matrix multiplication between this normalized similarity matrix and this matrix V. And this is essentially where this weighted feature averaging is happening. And this is a step that allows us to incorporate context from the entire sentence into the feature vectors associated with individual words. So, and as you can see, so the implementation is very simple, but by stacking the self-attention operation on top of each other many times, we can obtain these very powerful transformer models. So now you might be wondering, well, why do we care about the self-attention or these transformer models? Well, we care about it because at a high level, video understanding and natural language processing share several similarities. So for one, both sentences and videos are fundamentally sequential. So you would think that whatever model works well for natural language processing, to some degree, it should also generalize to video understanding. And more importantly, sometimes we know that in order to understand the meaning of the individual words, we have to look at a broader context and we have to look at an entire sentence. And similarly, you could argue that in order to understand the meaning behind of atomic actions in short video segments, we also need to leverage broader context and we need to look at an entire video context. And so this is basically why we believe that these long-range self-attention-based models would also be highly effective for video understanding. So that's kind of the motivation. However, if we look at the prior work in video classification, we see that most of these state-of-the-art models, they rely on some form of 2D or 3D convolutions for spatiotemporal feature learning. And despite the effectiveness of these 3D convolution-based methods over the last few years, we argue that they're not the best way to do video modeling because they're inherently designed to only capture short-range spatiotemporal dynamics. And in contrast, these self-attention-based models, they're much more flexible in the sense that they can capture both short-range and long-range dynamics. And so that's why we want to explore this direction. So now the key question is, how do we sort of pre-process the video so that we could feed it into these self-attention-based transformer models? So inspired by recent work on image classifications, what we do is we simply decompose the video into a sequence of non-overlapping frame level patches. We can then map each patch into a feature embedding using a linear projection, augment that feature embedding with a spatiotemporal position information. So essentially encoding where in the video this patch appears, both spatially and temporally. And then just basically feed the resulting feature embeddings into these transformer-based models. And so now this is nice because basically we can interpret these, the resulting sequence of vectors essentially as tokens that can be fed into the transformer model analogously to the tokens obtained from words in the natural language processing. So in a sense, we're able to recharacterize this video understanding problem into the same framework that is used for natural language processing. And the only limitation here is that, as I described a few slides ago, is that the standard self-attention, it requires computing similarity for every single pair of tokens, or in this case, every single pair of patches. And because typically for these video understanding models, we have to operate on frames of videos that contain more than 30 frames, the number of patches that we have becomes very large. And so this computing similarity for every single pair of those patches just becomes too computationally costly. And so this brings us to the main focus of our work, which is to design scalable space-time self-attention schemes. And so specifically here, we look at three different self-attention schemes: space-only attention, joint space-time attention, and then lastly, our proposed divided space-time attention. So let me first try to describe the space-only attention illustrated on the very left. So here, what I'm visualizing, this blue patch essentially depicts a query patch for which we want to compute this self-attention-based representation. And of course, in practice, we want to do this for every single patch. But here, just for illustrative purposes, I'm focusing on this individual case, just so that we could understand the differences between each of these self-attention schemes. And all these differently colored patches, so in this case, these red patches, they basically depict the self-attention neighborhood, that is used to compute this new representation for the blue query patch. And so in this case, because this is a space-only attention, as you can see, we're only considering patches that appear in the same frame as this blue query patch. And so the advantage of this scheme is that now we're significantly reducing the computational cost, because now we don't need to compute every single pair of patches. But unfortunately, we cannot do any temporal modeling in this case, just because we're only considering spatial dependencies. So on the other end of the spectrum, we have joint space-time attention here depicted in the middle. And so this is just basically a standard self-attention implementation, where now we're considering every single pair of patches. And as already discussed, so the benefit of this scheme is that now we can do full spatiotemporal modeling, but the disadvantage is that the cost of this scheme is very high, because we have to consider every single pair of these patches. And so to address these shortcomings, we then propose our divided space-time attention. And here the key idea is to basically factorize this joint space-time attention into two components, into a temporal and spatial attention. And so the spatial attention is still implemented in the same way as described before. But now, so we're basically just considering these patches in the same frame as this blue query patch. But now we also have this temporal attention illustrated by these green patches. And so now we're considering patches from all the other frames in the video, but only patches that appear in at the same spatial location as this blue query patch. And so the advantage of this is that now we can do both spatial and temporal modeling, but at the same time, we don't need to consider every single pair of patches, which makes this scheme much more computationally efficient than this joint space-time attention scheme. And so now if we compare their quantitative performance, so here we do that on the two popular action recognition benchmarks, namely Kinetics 400 and something v2. And here we evaluate the performance using a standard accuracy metric, so just basically computing the fraction of videos that were classified correctly. And so in this case, we do see that our proposed divided space-time attention, it outperforms both of these other self-attention schemes. And what's interesting to note here is also that this space-only attention, it actually performs quite well on Kinetics 400, even though it doesn't do any temporal modeling. And so for those of you who are familiar with kinetics, so this is not too surprising, because it is known to be a very spatially biased data set. And so in this case, we're showing that we can do well without any temporal modeling at all. But on the something v2 data set, which requires very heavy spatiotemporal reasoning, space-only attention performs very poorly. And you can see that our proposed divided space-time attention outperforms it by more than 20%, which indicates that temporal reasoning is very important for this data set. And in terms of computational cost, we also compare this divided space-time attention with the joint space-time attention. And so here, basically what I'm visualizing is the computational cost measured in T-flops as we increase the spatial resolution of the video, which is a plot on the left, or as we increase the video length, which is a plot on the right. And so here we show that our model scales reasonably well in both of these settings, but the joint space-time attention scheme, the computational cost just grows very rapidly to the point where we can't even use this model anymore because it just runs out of GPU memory. And so both of these kind of results, they validate the design that we have, because so now we have this model that's more effective and also more efficient. And so now we can compare it to the state of the art, so to all of these previous 3D CNN-based techniques. And here our model, which we named TimeSformer, from time and space transformer, we show that it achieves the best reported accuracy on kinetics 400 and kinetics 600 data sets. And again, this validates this initial hypothesis. So we started this talk by saying, well, maybe these 3D CNNs are not the best way to do video modeling, and maybe we can construct a better model using these self-attention operations. And here we show that this is indeed possible.
Could I ask a quick question about this?
Yes, yes.
Hi. Yeah, that sounds really reasonable thing to do. So obviously, if the camera is not moving in a video sequence, then you have this sort of natural patch correspondence through time,
Right.
unless there are objects moving in the scene, which might be interesting to detect. If the camera is moving, now a lot of the changes you're detecting are related to the camera motion, not related to any particular activity. So I wonder, you know, there's a million questions around this, but maybe I'll leave it up to you how to handle it. But yeah, I mean, one could imagine, for example, registering frames through time before you drew the correspondences between patches and things like that. I just wonder if you have any thoughts on that general topic.
Yeah. So I think this is definitely one of the concerns that we had when we designed this scheme. And I guess the idea here is that, so let me go back to these. So here, this divided space-time attention. So basically what will happen is that we're going to have this divided space-time attention block, and we're going to stack it on top of each other many times. And so our hope is that so basically what happens is that the model aggregates the spatial information, then it can do temporal reasoning, and then the process kind of repeats that. It again sort of aggregates spatial information, then does temporal reasoning, and so on. And so we're hoping that even if there's camera motion or large motion of objects, the model is still able to pick up on these patterns, and basically the patterns that indicate which action is being performed, just because it has the ability to do both spatial reasoning and temporal reasoning. So in this case, we're hoping that before temporal reasoning is done, the model will already pull relevant information into this blue query patch, so that even if there's some displacements, the temporal reasoning can still benefit from more global information within each individual frame. So that's kind of the idea. And of course, we can't tell if that's exactly what's happening, but by the fact that the model is performing pretty well, I think, yeah, it makes sense that it's learning to adapt to the data set. And by looking into this specific phenomena more thoroughly, maybe we could even improve the performance. So yeah.
Okay, thanks.
Okay, so let me, so in another experiment that I wanted to talk about here is basically this long-term video modeling experiment. And so one of the exciting things about this new TimeSformer model is that in comparison to 3D CNNs, which typically operate on video frames, on videos containing maybe from 16 to 32 frames, now we can model videos that are much longer. And so we can model videos that last for 96 frames, which is a significant departure. So here we basically want to see if this is beneficial for long-term video modeling. And so how we do this is we consider this instructional video set. It's a large-scale video data set that contains over 1 million instructional videos, where each video is basically 7 minutes long. And so in these videos, we have people just performing various tasks. For example, maybe making breakfast, cleaning a house, repairing a car. So the tasks that kind of require more long-term understanding of these videos. So it's difficult to understand what they're doing if they're just looking at a few seconds in the video, which is kind of what's currently done in the field. So we want to test if this model is useful for these kinds of scenarios. So we select about 1,059 of these long-term action categories. And we use this data set to basically construct our own benchmark, which in this case consists of 85,000 training and 35,000 testing videos. And as I already mentioned, on average, each video here lasts for 7 minutes long. So a significant departure from these previous benchmarks where most videos last from 5 to 10 seconds. And then we just simply train our model as before. And so let's take a look at some of the results. So here, let me explain what I'm illustrating in this table. So first of all, in here, we're comparing our TimeSformer model with the slow fast baseline. And so here, this single clip coverage, which is illustrated in the third column of the table, it basically depicts the number of seconds spanned by a single clip. And so the single clip coverage is essentially controlled by two variables, the number of input frames and also the frame sampling rate. So for example, for this first slow fast baseline, we're sampling frames with a rate of 1/8, so basically every 8th frame. And so it operates on 32 frames, and as a result, it can cover 8.5 seconds with a single clip. Similarly, for second slow fast baseline, so we can use a different sampling rate. So in this case, we can use a rate of 1/32. And so then by sampling the same number of input frames, now we can cover longer video extents. So now 34 seconds. And the number of test clips, which is illustrated in the other column, it basically depicts how many of these clips are needed to cover the entire input video during testing. So we want to do a fair comparison so that each of these methods would still see an entire video during inference. And so that's basically what this table is illustrating. And let's take a look at some of these results. So first, we showed that for a fixed single clip coverage, our TimeSformer model outperforms the corresponding slow fast baselines. And this just illustrates that in this case, this model is much better suited for long-term video modeling than these 3D CNN-based techniques. The second observation is that in this case, we observe that these longer range models, they tend to do better at this task, which again kind of indicates that this task really does require long-term video understanding. So we see that in this case that this best performing model, which spans about 100 seconds with a single clip, it achieves the best accuracy. And I think this is a very exciting result because I think this is a pretty overlooked problem. And one of the reasons for that is that it was very hard to look at these long-term video modeling tasks because these 3D CNNs, they're very computationally expensive and to the point where we can't really extend them to operate on more than 32 frames. So it's quite difficult to do that. So I'm hoping that this work will encourage community to work on these type of long-term video understanding problems. And lastly, so we also visualize what this model had learned. So basically the areas that it learned to pay attention to in the videos. And so here the visualizations make sense. So we see that the model it learns to pick up on relevant objects and hands. And of course, we would expect that because it has to use all of this information to do all of this complex spatiotemporal reasoning. But it's still nice to see that it sort of localizes all of these relevant areas in the video. So any questions about the first part of the talk?
Feel free to just unmute and ask your question.
So, may I ask one question?
Okay.
So I saw in the table the jointly spatial and time attention the performance is a bit worse than the divided. Yeah, do you have any intuitions? I thought it would be better because
so I think there's a few reasons. So one of the reasons, and I didn't have time to go into more detail, but the way this is implemented is that So joint space-time attention only has one attention layer, whereas divided space attention has two layers, temporal and spatial attention. So in a sense, it has more parameters and larger learning capacity. And this is nice because it's more efficient, but it also has larger learning capacity. So we're sort of getting the best of both worlds. And so I think that's one of the reasons. And the second reason might be that maybe this joint space-time attention is overfitting a little bit. So it's considering all of these different pairs, and maybe if we had a larger data set, this wouldn't be a problem. But so it's possible that maybe it's overfitting in this case. So I would say, yeah. So probably both of these contribute in some part to the performance.
I see. So another question is, you use the transformer, like the self-attention from the very beginning, the first layer to the end. So what if we mixture the convolution layer and the self-attention? Have you ever tried this? Will it improve the performance, or it has worse performance?
It's very similar. So yeah, so we tried it and it doesn't help. It's almost exactly the same performance.
I see.
Yeah.
I see. Okay, thanks.
Okay. So let me start.
Sorry.
Yeah.
So my question is related to overfitting. So I mean, these works on transformers for images tend to use a lot of data. I don't know, 400 million images and so on. But so I'm wondering, did you see specifically overfitting because of these these architectural choice? And another question that I have is, how many parameters does this model have in comparison to previous 3D models that you are comparing with?
I mean, so it has, so I didn't fully understand the first question. I guess I'll first answer the second question. And so it has a much larger number of parameters. I would say maybe, twice as many, but this is, again, I think this is not indicative of the actual cost, because I mean, the number of parameters is larger just because of the design of these models, but the cost is actually lower than these 3D CNNs. So I wouldn't say that the number of parameters in this case is an accurate metric to look at. And it's actually, I mean, in this case, it takes less time to train these models than the 3D CNNs under the same conditions. And I'm not sure what your first question was.
Oh, so my first question is general. I just wanted to have general discussion about, the amount of data required to train these models.
Yeah.
And I can see that since you're only doing this supervised learning, which you are severely limited by the amount of data. So I'm wondering, do you expect, larger improvement by more data, or pre-training helps, or,
Yeah, so yeah, pre-train. So we're actually using pre-training, and pre-training helps a lot. And yeah, so in this case, ImageNet pre-training, and yeah, so it's currently also the limitation of the model that it's we still haven't figured out how to train them from scratch, and this is kind of active work going on. But I think, yeah, as shown by previous papers, more data helps in these cases. But in this case, yeah, so if we use this, image level pre-training, so it actually still works pretty well on the video domain. So I think, yeah, but I think there's still, lots of different directions to explore related to these questions.
Okay, yeah, thank you.
Yeah. So let me go into the second part of the talk. And so here, basically the idea will be to use language to learn our visual representations. And to motivate this work, let me show you the following video where this famous chef Gordon Ramsay is teaching us how to make breakfast. And because of the instructional nature of this video, we're observing that his instructional speech aligns very well with the video content. So for example, he's talking about mushrooms, and the video also zooms into the mushrooms, or he's talking about frying tomatoes, and we also see in the video him putting these tomatoes in a frying pan. And so the main motivation here is to try to exploit this alignment between video and the instructional speech. And so specifically, the problem that we're going to be considering in this case is we want to learn a representation that would be useful to understand better how humans interact with objects. And this is an important problem because even just knowing which objects people are interacting with already provides us with lots of useful cues about their behavior. For example, what they're paying attention to, what kind of actions they're performing, what their intentions might be, and so on. And so when we look at this problem, the key challenge is that in the context of these human-object interactions, many objects exhibit extremely dramatic variations in their appearance. So for example, tomatoes, they can be chopped or halved, liquid or solid, fresh or fried, red or green. So many different states, many different actions that can be applied to it. And the goal of this work is to basically learn what we refer to as all of these contextual details behind human-object interaction. So all of these states and actions that can be applied to objects. And this is in contrast to prior work, which mostly trains these object detectors at a very coarse level, where label spaces are usually expressed in terms of nouns, such as egg, fish, plant, meat. And in here, in addition, in this case, in addition to being able to recognize that there's an egg in this image, we would also want to know its state, what action has been applied to it, and even what other accompanying objects are around. So that's kind of the goal. And we're not the first to look at this problem. So there's been some prior work in this area, but unfortunately, the key limitation that most of this prior work relies on manually labeled data. And when we consider this problem, this becomes problematic because even if we just consider a single object category to get all of the possible states, all of the possible actions that can be applied to, just the label space exponentially explodes. And if we wanted to manually label all of this data, it would just require lots of time, resources, and money to do this. So in my view, this is completely impractical and unscalable. And so that's why we want to move away from this framework of using human supervision and try to find alternative ways of training our visual models. And so again, to do that, we leverage this large-scale instructional video data set. So this how to 100 million data set, which contains over 1 million instructional videos, where now we basically have videos paired with automatically transcribed speech narrations where people are literally describing what they're doing in those videos. And so this is a perfect data set for our purposes because it contains lots of human object interactions. And now that we also have these more detailed descriptions of what people are doing with those objects. So in a form of these automatically transcribed speech narrations. And the only limitation of this data set is that it doesn't have bounding box annotations. And so in this case, to address this shortcoming, we use a very simple scheme. So we simply run a pre-trained object detector on the frames of how to 100 million, and we then consider the most confident object detections that also match the speech narration. So for example, if our visual detector says that there's a rolling pin in a given video frame, and also the speech narration mentions a rolling pin, we then consider that as a positive instance and we add it to our new data set. And this simple procedure allows us to collect 1.1 million pseudo ground truth bounding boxes for 154 object categories and about 560,000 frames of how to 100 million. And so now we have this very nice data set where we have bounding boxes of the objects, we have their coarse object level categories, and we also have more detailed descriptions of what people are doing with those objects. And so now we can use this data set to train our contextualized object embedding framework, which we refer to as COBE. So in this case, our system takes as input a video frame with an automatically transcribed speech narration, and we first feed the speech narration through a pre-trained transformer-based language model, which outputs a contextualized word embedding for every word in a sentence. And so as already described in the previous part of the talk, the key characteristic of these transformer-based language models is that now each of these contextualized word embeddings, they capture information not only related to the word itself, but also to the entire sentence. So for example, the feature vector associated with the word egg also captures information related to the contextual action of breaking and also a contextual object bowl. And so in a sense, this is exactly what we want to do, but in the visual domain. So just like these language models learn contextualized representations for words in text, we want to do that for objects in the visual domain. And so to do that, in parallel, we feed a given video frame through our visual detector model, which in this case corresponds to a modified faster RCNN. And so here, the key difference is that instead of a standard classification branch, which simply predicts coarse object level categories, we now have this contextualized object embedding branch, which outputs continuous vector representations for every detected object instance. And to guide these predicted object embeddings to be similar to the contextualized word embeddings obtained from text, we then use a contrastive loss function. And more specifically, this contrastive loss function can be expressed using the following formula, where here F is our predicted object embedding, G plus here depicts a positive word embedding that actually describes a given object, an object in a given video frame. And all these vectors associated with the G minus, they basically depict the negative word embeddings that are not related to the object in a given video frame. And so this loss function, in a sense, it forces our model to learn a visual representation that is similar to the positive word embedding and is dissimilar to all these other negative word embeddings. And by optimizing our model with respect to this objective, basically what happens is that the model kind of learns to align these visual and textual representations. And in the end, our final visual representation lies on the same manifold as all of these textual feature descriptors. And so because of that, afterwards, we can use COBE in various text-based applications. And the first application that we consider here is object-to-text retrieval. And so here specifically, given a visual query in the form of a detected object instance, we want to retrieve most similar text. And in this case, the text comes in a form of object context tuples, where object is a coarse object level category, and context can be any other word providing some contextual information about that object. And here we visualize some of these retrievals. So the green bounding box here depicts our visual query, and the text below is the most similar text retrieved for that visual query. And so as you can see from these results, the model is able to capture a diverse set of contextual cues. So for example, in column 1, we see that the model detects that there's onion and that there's a pan, but now it also knows that the onion is chopped, that the pan contains onions, and also that these onions are being sauteed. In the third column, similarly, we see that the model detects that there's a tomato in this frame, but now it also knows that this tomato is being sliced, that there's a knife nearby, and also that these are cherry tomatoes. So basically now, in addition to capturing these coarse object level categories, we're also able to learn these contextual details behind human object interactions. And similarly, we can also reverse this task, and instead of doing object to text retrieval, we can also do text to object retrieval. So here, given a textual query of the same form of object context tuple, we can retrieve most similar object instances in COBE space. And here we visualize some of these, the top retrievals. So every column here depicts a fixed object category, and every row depicts contextual information about that object. And again, we can see that the model is able to learn a variety of different information, for example, the functional properties of objects, their color, the actions applied to them, and so on. So for example, in column 2, for an object category sauce, the model learns different kinds of sauces, such as barbecue sauce, hot sauce, soy sauce. In the last column, we see that the model is able to learn different colors of peppers. So it learns all kinds of different information, which is exactly what we wanted. Any questions on the second part of the talk?
So,
okay.
Yes, I just have a quick question. First of all, this is great. This seems like a great way of learning richer representations. Can you say anything about generalization of concepts that haven't been directly observed? For example, if you've learned about chopped tomatoes, but you haven't seen chopped onions, is there any way that this model could generalize those kinds of ideas?
Yeah, so that's a great question. And it actually, so I didn't have time to present our results on that, but we do have those results in the paper. And it's actually, so it's able to learn some of these concepts. And the idea is that, I guess the language model sort of has these compositional properties that allows it to kind of generalize to these novel concepts. And what we're seeing is that by using the language model to supervise our visual model, some of these properties also transfer to it. And so we're able then to approach these zero-shot recognition problems, even for some of the states that we haven't seen before. And I think that's also a very exciting research direction for the future. Just a good way to learn these representations that could be used for few-shot or zero-shot learning.
Yeah, cool.
Okay, so we don't have too much time, so let me just quickly go through this last part of the presentation. And here, we're basically, our goal here is to design a higher level video understanding framework, and we view this problem as a language generation problem. And so this is a work done by our summer intern, Shuran Ling. And yeah, so this is a paper that was recently accepted to CVPR, and I'm excited to present this. So specifically here, we want to look at this. We want to look at these video-based text generation problems, and that operate on multimodal inputs. And so specifically, we're going to be considering 3 different problems: video captioning. So here, given these multimodal inputs consisting of video plus text, speech, and audio, our goal will be to generate a caption describing what's happening in that video. The second problem that we're going to be looking at is the video question answering. So now, in addition to these previous inputs, we might also have a question as part of the inputs, and then the goal will be to generate an answer to that question. And last problem will be video dialoguing. So now, instead of a single question, we might have a dialogue history, and then the model will have to look at that and basically generate an answer in response to the last question of the dialogue history. So those are the 3 problems. And before I start describing the method that we designed for this problem, I also briefly wanted to talk about some of the prior work. And so this is a pretty new sub-area of computer vision. So there's not a lot of work done in it, but there are a few methods and they're quite successful. So I briefly wanted to talk about some of their limitations. And so specifically, I'll talk about this recent HERO system, which is illustrated in this slide. And so one of the limitations, as you can probably infer from this slide, is that this is a pretty complicated system. So it contains lots of different components. It might be difficult to use and maintain and generalize to new settings just because of the complexity of the system. And so one of the reasons why this system is complicated is because exactly of this multimodal nature of the problem. So basically, every time we need to combine different modalities, the authors of this work just design some specific submodule to do this cross-modal fusion. And so if we have multiple modalities, you can imagine that this can quickly become into a very messy architecture. And so indeed, in a sense, that's a little bit what's happening. And so one of the motivations of our work is that we want to simplify this entire pipeline while still maintaining strong performance. So that's going to be one of the motivations. And the other limitation of this work is that it also requires this large-scale multimodal pre-training. So basically, the authors in this work, they have this paired video and text data set, which is first used to pre-train the model for some pre-text task, and then that representation is used to fine-tune the model for the target tasks. And again, we kind of want to eliminate this step because, for one, we will not always have access to such large-scale multimodal data that generalizes to our target tasks. And for 2, it's a very computationally heavy step. And so especially for research labs with fewer computational resources, it would be unfeasible to do this large-scale multimodal pre-training. And so the inspiration for our work comes from these modern language models. And so I already talked briefly about it. But so specifically here, what we're interested in is these models that are designed for text generation problem. And so in the last few years, we have seen models such as T5 and GPT, which can generate really realistic text, which looks very similar to how humans would generate text. And so our idea, instead of reinventing the wheel and trying to design these very complicated cross-modal architectures, we simply want to incorporate these generative language models into our video-based text generation system. And so the idea is that it would allow us to simplify the problem, to simplify our framework while also leveraging the strengths of these very powerful language models. And so the key technical challenge then becomes is that in this case, we're not just operating on text, we're actually operating on multiple modalities. So the question is how we can fuse all of these modalities so that this language model would be basically able to incorporate all of the relevant information for the target task. So that's kind of the challenge. And let me now present how we address this challenge. So we present this VX to text approach, which operates on multimodal inputs consisting of video plus text, speech, and audio. And it's then supposed to output a free-form text corresponding to our target task. So one of the video captioning, video question answering, or video dialoguing tasks. And so one of the things that I haven't discussed here is that in this case, so as I mentioned, we want a simple framework, and we also want a framework that can address all of these tasks with a single model architecture, which again is different to prior work, which basically they have to design slightly different architectures for each of these tasks. And so to simplify this pipeline, so instead of modifying architecture, we propose to use this specialized task token. So basically, if we want to solve for video captioning tasks, let's say we can encode this special task token. We can say that it's captioning, feed it as part of the inputs to the model, and then the model will take a look at it, and it will then know that in this case, it needs to solve for video captioning task. Similarly, if we're interested in question answering problem, this special task token can be formulated as answer the question. The model will then take a look at it, and it will know that now it needs to answer a question. And so with this very simple scheme, now instead of modifying the architecture, we can address all of these tasks by just simply modifying the inputs to the model, which I think it's very practical and simple to use. And so now we can actually look at some of the steps, how this entire framework is implemented. So as a first step, we process each of these different modalities using a modality-specific classifier that was previously pre-trained on some classification task on a predefined set of categories. So for example, for video, as I already discussed, we have a lot of these pre-trained action recognition models, which take a video and they can output one of the action categories, such as maybe a person running, dancing, and so on. So we use one of those models. Similarly, for audio, we can also use one of these pre-trained models. So there's a lot of them that basically they take sound as an input and then map it into one of the sound categories, such as maybe a man is talking, a dog is barking, baby crying, and so on. So we use these pre-trained models. And then the key question then becomes how we can integrate the outputs from these modality-specific networks into a unified language space so that our language model would be able to incorporate these modalities for the target task. And so in this case, we use a very simple two-step procedure. So basically what we do is we first probabilistically sample the K categories from each of these predicted categories from each of the modality-specific classified. And then afterwards, we can take the names of these sampled categories and use a fully connected layer to map them into a unified language space. And so this basically allows us to map these modality-specific inputs into this unified language space, which can then be fed into our generative language encoder-decoder model. And so, and this generative language encoder-decoder model then generates the text corresponding to our target task. And so here the idea is that the encoder, its responsibility is to basically incorporate modality-specific signals. So it has to incorporate them for the target task. And so as you can imagine, for example, for video captioning, maybe the model needs to mostly pay attention to the video content. And so then the encoder, it knows that in this case, because the task is video captioning, it mostly pays attention to video. But for question answering, it also needs to pay a lot more attention to the question. And so now the encoder, given this task, it knows basically to pay attention to both video on the question and also other modalities if they're relevant. So basically what we're saying here is that the encoder does all the heavy lifting for us. It incorporates multiple modalities and essentially does this multimodal fusion instead of us having to design all these complicated cross-modal architectures. And then the decoder takes this representation and it just outputs the text for a target task, and it does so in an auto-regressive manner, meaning that it reuses the previously generated words to generate the next words. And so this is important because it basically allows our model to generate these very smooth and realistic text sequences. And so afterwards, we can then just simply optimize this entire model end-to-end using a standard cross-entropy loss function. And so one of the things that I haven't covered here is that in this case, because we take special care of maintaining differentiability in this entire model, so the entire model is end-to-end trainable. So we can propagate the gradients through the language model and even back to these modality-specific classifiers. So now they can adapt to the target task instead of just having this fixed pre-trained representation. So let me now go over through some of the results. So first, we'll look at the dialogue generation results. And here, this is evaluated on AVSD dataset. And the performance is evaluated just using standard text generation metrics. And so here, what I'm visualizing, so every bar plot here depicts a different evaluation metric, and every bar depicts a variant of our model that uses a different subset of modalities. And there are a few interesting observations here. So for one, so this blue bar, it essentially depicts a text-only baseline where we're only feeding a question and a dialogue history to the model. And here we basically want to show that the text alone is not enough to solve this problem. And we do see in this case that this variant of our model performs quite poorly. And the second bar, this orange bar, it's basically a variant that also uses video. And you can see that in this case, just by adding video, we're getting a big boost in performance. And so afterwards, all these subsequent bars, it's just basically adding other modalities. And so we can see that we can get a boost in performance. And so this shows two things, that this is a truly multimodal problem, and also that our model, in a sense, even though we don't have any complicated architecture, it still learns to incorporate signals from each of these modalities, and it leads to better performance. And here, so I'm not going to go too much into detail here. This is just basically showing that we can outperform these previous methods by a pretty significant margin in this case, according to all metrics. But I think what's really interesting is looking at some of these qualitative results. And so here, take a look at the video sequence on the left. And so here, what's truly amazing for me is that the model is able to do very well, even in these very uncertain scenarios where I think a lot of humans would actually struggle. And especially if you look at this last question where, as you can see, it asks what's on the table next to her, our model generates the answer that says, I can't tell what is on the table. And I think this is pretty interesting because most of these models that we're used to, they just take a random guess in those cases. But in this case, this model kind of generates a human-like response. And in a sense, it makes sense because the model is trained to kind of mimic how humans respond in these dialogue settings. But it's still pretty amazing that in this case, I think it would be quite difficult to differentiate between human-generated text and machine-generated text. And similarly, we also see state-of-the-art performance on video question answering tasks. So in this case, it's evaluated on the TVQA dataset. And in this case, the performance is evaluated just using a standard accuracy metric. And we do see that in this case, we can outperform all of these previous baselines, including the state-of-the-art hero baseline, even though we're not using this large-scale multimodal pre-training. So I'll skip the slide since we don't have too much time. This is just more qualitative results that kind of show, how well this model can perform. And yeah, so to summarize, so we started this presentation by trying to look at these 3 different angles, how we can use language models for designing better video understanding frameworks. And so first, we looked at this idea of applying language models to video understanding, so mainly to an action recognition setting. And we presented this TimeSformer model, which provides a fundamentally different way to do video modeling, and it achieves best reported results on several action recognition benchmarks. Afterwards, we looked at this idea of using language as means to supervise our visual model. And so we showed that instead of relying on human supervision, in this case, we can use this automatically transcribed speech narrations from instructional videos and obtain this pretty good visual representation that allows us to better understand how humans interact with objects. And lastly, I then looked at this problem of higher level video understanding, and we showed that by posing it as a language generation problem, we can address 3 different problems and obtain state-of-the-art performance in each of them. And so before I finish, I want to also to acknowledge my collaborators which contributed to this work. And now, I don't know if we have any time, but I'd be happy to answer any remaining questions. Thank you.
Feel free to unmute and thank our speaker.
Hi, Gedas. I had a couple of questions.
Sure.
So the first thing is during the pre-training, you're pre-training with multiple modalities and you're using a task token to differentiate between different modalities, right? Then I was not clear how exactly the examples are set up. Do you have all the 3 modes for every example, or do you have only some modes for some examples and not the others?
Yeah, so it depends on the task. So in some tasks, we might not have, we might not have transcribed speech, for example. So we just use any modality that we have. But so for, like for example, for dialoguing, we have most of these modalities. So we have dialogue history, audio, speech, video. But yeah, if we're missing modalities, so then we're just not going to use it.
Okay, so you always distinguish between different modalities in the example, or do you just have one sequence of vectors?
Yeah, so the modalities, they are distinguished in this case. And I think if you trained a more general system, then maybe, you could avoid that.
Okay.
So in this case, we're kind of still optimizing for these tasks.
Okay. The second question is about the, about the results of different models using different modalities. You said just text, which is the history, was giving you not great performance, but then when you added in the video, it improved. And then, so I'm trying to understand why audio is helping at all, because the audio transcriptions already going to be in the history, right? So what aspects are there in audio that actually helps?
Well, sometimes, maybe, I mean, so like if a dog is barking, the speech transcription is not going to have that. And so, I think there's a lot of these kind of, I guess, like we don't understand how useful audio can be, but I think, it's pretty useful usually. And it's not the most important modality, but it still has some useful signal.
Okay, cool. All right, thank you.
Any other questions?
I just want to add, there's a couple of empty slots from some cancellations in Gedas's schedule. So either email me or Contextualized, we can help you with that if you have kind of more in-depth questions to discuss. But otherwise, we can just thank our speaker. Feel free to unmute. Thanks.
Thank you.
Thanks.
And I guess your first meeting is it was supposed to be at 2 o'clock, but then there was a cancellation. If there's an update and someone signs up, I'll definitely let you know. But otherwise, it's going to be 2:30. Yeah.
Sounds good.
Awesome. Thank you so much. This is a great talk.
Oh yeah, thank you. It's a different Zoom link for the meetings, right?
It is, yeah.
Okay, yeah.
But it
Yeah.
should be in the email that Kalpesh sent.
Okay, yeah. Thank you for inviting me. Yeah, great to be here.
Yeah, thank you so much for joining us.
Okay, bye.